Welcome back to the deep dive. Today we are putting our surgical loops on and diving into the deepest layer of orthopedic precision, in vivo kinematics of total knee arthroplasty.
That's right.
Forget the simple x-ray you see in the clinic, the one showing 100 degrees of flexion. Our mission today is to analyze what the TKA components are really doing under dynamic weight-bearing load.
It's the difference between looking at a beautifully aligned implant on a static AP X-ray and catching it mid-step, trying to figure out if it's performing a graceful waltz or slipping on a banana peel.
Huh, I like that. A waltz versus a banana peel.
For too long, we've relied solely on these subjective clinical outcomes. But if we're serious about the ongoing goal of improving longevity and satisfaction rates, if we want to move beyond, say, 95% good results to 98%,
Which we do.
we need accurate measurable data on function. We need the actual in vivo kinematic analysis.
Absolutely. We need to know, is the femoral condyle rolling back symmetrically? Is the polyethylene insert rotating freely? Or is it trying to pull a disappearing act inside the joint?
And the knee joint is not a simple hinge. I think that's the biggest misconception.
Not at all. It's a beautifully complex 4-bar linkage system. So when we replace it, we need a key that not only fits, but also turns perfectly through that entire range of motion, managing roll and glide at the same time.
And that dynamic moment, that real-time movement under physiological load, that is precisely what fluoroscopy delivers. It is our current gold standard for this kind of work.
Okay, so break that down.
Think of it. You're using traditional X-rays to create a video. It gives us a two-dimensional visualization of the joint across the entire activity.
It's like trying to analyze the complex movements of a piston in an engine, but instead of, having the engine block open, we're looking right through the patient.
That's a great analogy.
It gives us the motion, but I imagine the real technical challenge is turning that flat, fuzzy 2D shadow into precise, measurable, three-dimensional data that we can actually trust. Down to a fraction of a millimeter.
Precisely, and that's what we're going to get into. Today, we're going to start by reviewing why our historical methods, some of which are still used in some places, simply aren't adequate for the precision we need. Then we'll dive deep into the technical process itself, the C-arm choreography, the computer-aided design model, superimposition, and all the mathematical magic that extracts that 3D reality.
And finally, the payoff. The data.
Yes, finally. And this is the most critical part. We'll dissect the hard kinematic data. We'll look at antero-posterior translation, axial rotation, and the wear-inducing phenomenon of condylar liftoff.
All right, let's get into it. So let's set the stage. If fluoroscopy is the answer, why did it take us so long to adopt it? And I guess what were the major limitations of the techniques we relied on before?
Well, historically, we relied on 4 major approaches: cadaveric testing, non-invasive surface marker systems, Röntgen stereophotogrammetric analysis, or RSA, and of course, magnetic resonance imaging, MRI.
And each one gives you a piece of the puzzle, but not the whole picture.
Exactly. None of them can capture the dynamic, precise, and weight-bearing nature of a living, functioning knee replacement.
Okay, so let's start with cadaveric studies. In theory, they seem like a good place to start. You can control everything, all the variables. So why do they fall short in replicating what happens in vivo?
They fall victim to what I like to call the dead knee dance problem.
The dead knee dance. I like that.
Yeah, you just can't teach a dead knee how to dance. I mean, while you can control the forces to some degree, you cannot replicate the nuanced, coordinated action of physiological muscle forces.
Right.
The mechanical actuators we use to simulate muscles,
Right.
they just don't replicate in vivo motion. And the complex interaction of the soft tissues, the ligaments, the capsule, all of it.
So if the knee is being controlled by, say, a system of pneumatic pistons that are mimicking the quads and hamstrings, those pistons are working in isolation. They're not getting the same feedback a living person's muscles are.
That's exactly right. The forces aren't physiological, which means the resulting kinematics we measure in a cadaver might not reflect the forces and movements we see when a real patient performs a step up or pivots. The boundary conditions are just fundamentally different.
Okay, so that's cadavers. What about the non-invasive options? I'm thinking of the surface marker or gait lab systems. They're great for measuring overall body movement, right? But what happens when we zoom into the joint itself?
When we zoom in, we hit the wall of the soft tissue artifact.
And that wall is pretty much insurmountable for the kind of precision we're talking about.
It really is. The soft tissue artifact is the critical flaw. It's the movement of the skin markers relative to the underlying bone. Think of it like this. You're trying to track the movement of the femur by putting a tiny flag on a loose, baggy sleeve of skin and fat.
And as soon as the patient moves, especially with rotation, that flag or that marker, it just shifts dramatically relative to the actual bone it's supposed to be tracking.
Precisely. And this artifact introduces significant out-of-plane rotational and translational errors.
Yeah.
Now, those errors might be acceptable if you're analyzing the general gait cycle of the hip or the ankle, but when you are evaluating the femorotibial articulation in terms of millimeters of rollback,
It's a non-starter.
it just renders the data inaccurate. We need millimeter and sub-millimeter precision, and surface markers just can't deliver that through loose tissue.
Okay, let's pivot to the gold standard of precision, even if it is invasive. Röntgenstereophotogrammetric analysis, or RSA. I know we use this for micromotion studies, but what stops it from being useful for dynamic kinematics?
Well, RSA techniques are generally the most accurate and precise method we have,
Yeah.
no question. They involve implanting these tiny metallic markers, usually tantalum beads, directly into the bone. And then you use two specialized X-ray cameras to create a 3D reconstruction. The precision is phenomenal, often less than 0.1 millimeters of error.
So if it's that precise, why can't we just take a high-speed video using RSA? What's the catch?
There are two fundamental reasons. First, the marker implantation is highly invasive, so we can't just use it routinely on every patient.
Of course.
Second, and this is more important for a kinematic study, these tests are conducted under quasi-static conditions. They are essentially a series of stopped snapshots. You capture the position at 10 degrees, then 20, then 30, and so on.
So it's capturing discrete, stopped points in the motion, but not the smooth, fluid transition between those points. The instantaneous center of rotation, the actual path of the knee, that's lost.
Exactly. You lose the fluidity of the movement itself. You can't analyze the rate of movement, the instantaneous velocity, or how the soft tissues react during the motion, especially as they cross, points of instability. It's a beautifully detailed still photo, not a high-definition movie.
And finally, MRI. I think we all know this one. It's great for soft tissue.
Terrible for dynamic analysis. MRI testing, as we use it clinically, is almost always conducted under static, non-weight-bearing conditions.
Right.
A static image of a knee resting in the bore of a scanner cannot tell us how a mobile bearing insert is functioning when the patient is rising from a chair and generating 3 times their body weight in force. The kinematics are completely absent.
So the goal is clear. We need a system that is accurate like RSA, minimally invasive, dynamic unlike RSA and MRI, and free of that soft tissue artifact that plagues the gait labs.
And that's the perfect niche carved out by fluoroscopic analysis.
Okay, let's get into the mechanics of it then, because the sophistication of this registration process, that seems to be the key that lets us bridge the gap between that fuzzy 2D video and the 3D precision we need.
It absolutely is. So we start with the data collection. The setup often involves a single fluoroscope, a C-arm position to capture the joint.
Right, and the subject is performing some functional activity, a deep knee bend, a step up, walking.
Exactly. And the key is to keep the knee joint centered in the field of view, ideally in the sagittal plane. As you can see conceptually in figure 17.1, we're recording the joint through the entire weight-bearing movement. The video is usually captured at 30 or 60 frames per second.
But that raw image, it's not perfect, is it? It has flaws.
It's not perfect. It suffers from inherent geometric flaws, which brings us to the first mandatory technical step, distortion correction.
These distortions, like pincushion and spiral distortion, they make the image fundamentally unreliable for measurement until they're fixed. It's like trying to use a ruler on a rubber sheet.
That's a perfect way to put it. Whether you're using an older analog image intensifier or a modern digital flat panel detector, some level of distortion exists. If we don't meticulously correct these effects, we can't trust any measurement of distance or angle. We'd be drawing straight lines on that wavy paper you mentioned.
So how do we calibrate the system to account for that waviness?
We use what are called fiducial control markers. These are physical objects, typically a grid or a plate that has metallic beads in a very precise, systematic, and known spatial arrangement.
Okay.
We X-ray this physical grid, and then we use the discrepancy between the known, true geometry of the grid and the distorted captured image to create a transformation map. This map allows us to transform every single pixel of the fluoroscopic image until the modified image correctly matches the undistorted grid.
So before we even look at the patient's knee, we run a calibration using a sort of checkerboard of metal beads to make sure the virtual space is perfectly square. That's the foundation.
It's non-negotiable. And that corrected image is now ready for the core process, 3D to 2D image registration. This is the real magic trick, where we reconstruct the 3D position and orientation of the implant components from a single flat 2D image.
And this requires inputting the exact specifications of the implants themselves, right?
Exactly. We start by creating a virtual environment within a computer graphical user interface, a GUI. In this virtual space, we place a virtual camera, which represents the X-ray source, and a virtual image intensifier, which represents the plane of our processed X-ray image.
We then import the 3D computer-aided design, or CAD models, of the TKA components, the femur and the tibia, and place them virtually in that space.
Yes, and the computer then uses iterative techniques to manipulate the 3D position and rotation of that virtual CAD model until its projected silhouette perfectly superimposes or matches the actual implant component silhouettes we see in the 2D X-ray image for that specific frame. You can see this set up conceptually in Figure 17.2, showing how those virtual components map onto the fluoroscopic space.
But I'm still stuck on this. How does a single 2D image tell us the depth or the out-of-plane rotation of the components?
That's where the principle of parallax comes into play. It relies on the physics of the X-ray beam. Objects closer to the radiation source appear larger and more magnified on the image intensifier than those that are further away.
Okay, so if the CAD model's projected shadow is, say, larger than expected, the software knows the component must be positioned slightly more anteriorly, closer to the X-ray source.
You got it. By analyzing how that projected shadow changes its shape, size, and location, even with flight movements, relative to the known geometry of the CAD model, we can infer and calculate those critical out-of-plane translations and orientations.
And that's how we get all 6 degrees of freedom, 3 translations, 3 rotations.
That's how we extract 3D in vivo kinematics from that single 2D image. Figure 17.3 actually demonstrates this process visually, showing the precise registration of the 3D model to the 2D image at specific flexion angles.
That sounds incredibly computationally intensive and, I imagine, prone to human error if you were doing it manually.
Oh, it was initially very laborious. It used manual matching or early template matching techniques. But the field has largely moved to iterative, computer-automated model-fitting techniques, which are both faster and they minimize the inherent variability and error that comes with human judgment.
So what's the standard optimization algorithm that's used to make sure we get the best possible match between the virtual model and the actual image?
The robust technique utilized is often known as simulated annealing. It's an optimization procedure, an energy minimization routine, that the computer uses to maximize the correlation value between the virtual CAD silhouette and the physical implant silhouette in the image.
So the software is constantly trying tiny variations in the 3D position until it finds the configuration that produces the best possible overlap, or the minimal energy.
That's it. It's not guessing. It's systematically minimizing error until it finds the mathematically optimal fit. And the resulting accuracy is what gives us confidence in the data.
And what does that accuracy look like?
Well, the proof of concept is in the error analysis. Unbiased tests consistently show that the automated model fitting process is incredibly precise. We're talking errors of less than 0.5 millimeters for in-plane translations and less than 0.5 degrees for rotations. And while the out-of-plane measurements inherently have slightly higher errors, they're still well within the range we need for meaningful biomechanical analysis.
Now, there's a major radiolucent elephant in the room, the polyethylene bearing. The X-ray beam goes right through it. How do we track the movement of the polyethylene, which is so crucial for mobile bearing designs?
That's a critical challenge, especially when we're monitoring the axial rotation and migration of those mobile inserts. Since the polyethylene itself is invisible, we have to rely on strategically placed radiopaque markers.
So this requires using specially designed bearings.
It does. We have to use specially designed polyethylene bearings that contain a minimum of 3, but ideally 4, precisely located metallic reference beads.
So we're chasing tiny metal footprints inside the bearing itself?
Precisely. As you can see in Figure 17.4, these beads are visible in the fluoroscopic images, and their known 3D locations are incorporated into the CAD model of the insert. By registering the virtual beads to the actual beads in the image, we can accurately determine the transformations and migrations of that polyethylene insert relative to the tibial tray. Without that, we lose all insight into the performance of mobile-bearing TKAs.
Okay, so single-plane fluoroscopy provides fantastic precision, but the field hasn't stood still. The next generation of this technology attempts to address the 2 main remaining limitations, that little bit of out-of-plane error and the constraint on patient activity.
Let's start with biplanar fluoroscopy, which directly attacks that out-of-plane error associated with a single C-arm setup. It uses 2 offset fluoroscopy units, 2 X-ray sources, and 2 image intensifiers to analyze the knee at the same time.
So if you have two different perspectives, you essentially eliminate the guesswork required by parallax alone because you have two known lines of sight converging on the components.
That's the benefit. By incorporating 2 views, the errors are significantly reduced. Biplanar fluoroscopy has reported translation errors as low as 0.36 millimeters and rotational errors of 0.42 degrees. It makes it arguably the most precise method we have, short of invasive RSA. And you can see a schematic of this complex dual setup in Figure 17.5.
That increased fidelity sounds ideal, but I'm imagining two massive pieces of equipment in the room. I mean, the patient's freedom of movement must be severely restricted.
And that is the trade-off. The space constraints imposed by the 2 units limit the activities that you can analyze. We might capture a deep knee bend or a stationary lunge perfectly, but trying to capture full gait cycles or complex activities like stepping over obstacles becomes physically impossible. The equipment just crowds the subject.
Which brings us to the most exciting advancement for clinical relevance, the tracking fluoroscope system, or TFS. This seems to solve that activity constraint problem entirely.
The TFS units are a game changer for capturing natural motion. They let us move beyond these constrained lab movements. These are robotic units, like the one shown in Figure 17.6 at the University of Tennessee, that are programmed to actively follow the patient around the room.
So the system is tracking the joint, let's say the center of the knee rotation, and the C-arm is constantly adjusting its position and angle to keep that joint centered in the field of view, no matter where the patient goes.
Exactly. The system moves with the patient as they perform a complex activity. This means we can evaluate true, unconstrained, and highly natural activities. Walking multiple gait cycles, going up and down ramps, or doing a set of stairs.
And this yields results that are far more representative of a patient's daily life compared to a single, static, deep knee bend in a confined space.
Far more accurately. The data is invaluable because it removes the inherent bias of laboratory-constrained motion.
But we can't discuss fluoroscopy without addressing the significant ethical imperative here, radiation exposure.
That is the primary overarching concern with this methodology. We are essentially giving the patient a series of dynamic X-rays. So our commitment as investigators must be the absolute minimization of patient radiation time and exposure.
What are the practical steps we take to mitigate that exposure?
First, we are extremely stringent about setting and adhering to maximum exposure limits. We calculate the dose per activity, and we ensure the cumulative dose remains well within established safety guidelines.
Okay.
Second, and this is crucial, the patient must know exactly what activity they are performing. There can be no hesitation or practice during the actual X-ray capture.
So you rehearse the activity beforehand without the X-ray running to make sure the patient performs it smoothly and quickly when the beam is on.
Precisely. Rehearsal minimizes unnecessary exposure time that would otherwise be spent just figuring out the task. And actually, the TFS units contribute to safety here. Because they accurately track the joint, the entire set of activities can often be performed successfully in 1 or 2 highly efficient trials, which significantly reduces practice and capture time compared to wrestling a patient into a stationary C-arm setup over and over again.
And finally, standard radiologic safety measures still apply, even though we're just focusing on the knee.
Of course. Patients may opt to wear lead shielding over their hips, chest, and thyroid. That prevents unnecessary systemic exposure. So with rigorous protocol, constant monitoring, and the use of efficient technologies like TFS, the radiation exposure is easily minimized and is, clinically justified by the crucial kinematic data we gain.
All right, now we get to the payoff. All that technical rigor we just discussed was dedicated to generating this data. We are looking at sample results from a comprehensive study of 1,630 knees normal, ACL deficient, various types of TKAs and UKAs, all performing a weight-bearing deep knee bend. Let's start with anteroposterior, or AP, femoral tibial translation. That's summarized in Table 17.1.
This is the core movement we try to replicate, the femoral rollback. If the femur simply slid forward on the tibia, the muscles would be highly inefficient and the patient couldn't achieve deflection. So this translation pattern tells us if the implant is functionally replacing the natural geometry and soft tissue restraints.
So in a normal, healthy knee, what is the expected pattern of rollback as the knee flexes from full extension to 90 degrees?
In the normal knee, we observe posterior motion or rollback of both condyles throughout flexion. But here's the critical asymmetry. The lateral condyl's motion is significantly greater than the medial condyle. The average lateral condyle rolls back substantially, about minus 16.4 millimeters.
Hmm.
Meanwhile, the medial condyle rolls back only about minus 8.9 millimeters.
And that difference, that greater rollback on the lateral side, is what facilitates the essential axial rotation, the screw-home mechanism. The normal knee is not symmetric. The lateral side is doing most of the work in terms of translation to accommodate that rotation.
Precisely. And crucially, subjects with a normal knee rarely, we're talking only 2% of the time, experience any significant anterior slide with increasing flexion. The soft tissues are robust enough to prevent that paradoxical movement.
Okay, and when we look at ACL-deficient knees, the ACLD group, the basic pattern remains, but the stability is obviously compromised.
They exhibit the same differential rollback pattern, but with reduced magnitude. The lateral side rolled back about minus 13.3 millimeters, and the medial side minus 5.9. And logically, these knees sit slightly more anteriorly throughout flexion compared to normal knees, which just demonstrates the primary role of the ACL in static positioning and early flexion stability.
Okay, now, let's move to the main event, the TKA data. The general observation across all the designs is a dramatic reduction in motion.
A stark reduction. The average posterior motion across all TKA types was minimal compared to the native joint. We're looking at only minus 5.8 millimeters for the lateral condyle and a mere minus 1.9 millimeters for the medial condyle.
That's a fraction of the minus 16.4 we see in the normal lateral condyle.
It is. This limited motion is often why patients report that their replaced knee feels tight or clunky in deep flexion.
And what immediately jumps out is the massive variability depending entirely on the implant philosophy. The kinematic results are not uniform across implant manufacturers or designs.
The variability is staggering. The amount of average posterior rollback of the lateral condyle, depending on the TKA type, ranged from as little as 1.3 millimeters of posterior motion to a maximum of 21.9 millimeters. This really highlights that TKA designs fundamentally dictate the patient's biomechanics, often overriding individual surgical nuances.
We have to stop here and define the terms used in the study because the data is categorized by design philosophy. We see PCRF, PCRM, PCSM, PSM, and BCSF. Can you quickly break down what those acronyms imply for us?
Certainly. These terms classify the implant based on two things: whether they retain or substitute the posterior cruciate ligament, the PCL, and whether the bearing surface is fixed or mobile.
Okay.
So PCR is posterior cruciate retaining. These designs leave the PCL intact. PCRF is posterior cruciate retaining, fixed bearing. PCRM is the same, but mobile bearing.
Got it.
Then you have PS, or PCS, which is posterior stabilized or posterior cruciate substituting. These designs remove the PCL and substitute its function with the mechanical cam and post mechanism. So PSM is posterior stabilized, mobile bearing, and PCSM is the same idea.
And the last one? BCSF.
BCSF is by cruciate stabilizing fixed bearing. This is a newer, highly constrained design meant to replicate the function of both the ACL and PCL.
Perfect. Now that we have the vocabulary, let's look at the most concerning finding: paradoxical anterior slide. This is when the femoral component glides forward instead of rolling back as the knee flexes.
This is a major sign of mechanical failure and stress. It indicates the design geometry or the soft tissue balance is failing to restrain the femur posteriorly. Overall, 14% of all TKA subjects experienced anterior slide.
14%. That's 7 times the rate we see in normal knees. That's a massive kinematic deficiency.
It's huge. And the data shows that certain designs average an anterior slide on the medial condyle. That's not an occasional finding. That's the mean movement for those knees.
That's the key takeaway from Table 17.1, isn't it?
It is. 4 of the 7 TKA types analyzed, specifically the PCRF, PCRM, PCS, and PSM, showed average positive, meaning anterior, translation for the medial condyle. Take the posterior cruciate retaining, fixed bearing design, the PCRF. 24% of subjects experienced anterior slide. For the mobile bearing variant, the PCRM, it was 25%.
Why is this paradoxical slide so detrimental clinically? If the femur is sliding forward, what is the patient feeling and what is the implant experiencing?
Well, the patient may experience mid-flexion instability, the sensation of the knee giving way, or what we sometimes call a clunk. Mechanically, that anterior translation is resisted primarily by the collateral ligaments, forcing them into unnatural tension.
And I assume it can also cause the femoral component to articulate on the wrong part of the tibial bearing.
Exactly. It can cause it to articulate on the anterior, less conforming edge.
Yeah.
This generates high contact stress and initiates early polyethylene wear, which can potentially lead to osteolysis down the line. It's essentially the opposite of what the knee is engineered to do, like a gear slipping.
So those designs that retain the PCL, the PCRF, and PCRM, they rely on that ligament for stability. But if the PCL isn't tensioned perfectly, or if it stretches over time, that's when we see the highest rates of failure in AP stability.
That's the strong implication from this data. PCL retention requires masterful ligament balancing, and if that balance is imperfect, the inherent geometry of the components often fails to compensate, which leads to that anterior movement.
Now, let's talk about the kinematic superstar in this data set, the bicruciate stabilizing fixed bearing, or BCSF TKA. It achieved near normal or even supernormal rollback and critically 0% anterior slide. Why did this constrained design work so well?
The BCSF design is exactly what its name implies. It's highly constrained. Unlike standard PS designs that only substitute the PCL with a single cam post mechanism, the BCSF system incorporates a very deep, conforming articulation between the components. It effectively replaces the function of both the ACL and the PCL. The components are just geometrically locked together much more tightly.
So where other designs are relying on soft tissues that may be imperfectly balanced, the BCSF design forces the kinematic outcome through mechanical constraint.
It acts as an internal brace. That constraint forces the femur to roll back and internally rotate. And that yields a massive minus 21.9 millimeter rollback laterally and minus 12.5 medially.
Those numbers not only mimic, but actually exceed the average normal knee kinematics.
They do. It shows that if you eliminate kinematic freedom through high constraint, you can achieve highly reproducible, desirable motion. And this is a crucial finding that really challenges the philosophy of aiming for minimally constrained, kinematically aligned replacements.
That's a huge philosophical debate right there. Is enforced, constrained perfection better than variable, potentially deficient freedom? It suggests the mechanical limits of the implant matter more than our ability to balance the residual soft tissues.
For AP translation, this data strongly supports constraint. However, we do have to look at the trade-offs, which we'll discuss when we get to rotation.
Before we move on, let's quickly look at the unicondylar knee arthroplasty, the UK, results.
Right. The UKA subjects, which only replace one compartment, usually the medial one, showed more posterior motion than the average TKA, about minus 6.3 millimeters lateral, minus 4.4 medial.
Which makes sense since the unreplaced compartment is acting more naturally.
It does. However, the frequency of anterior slide was still greater than in normal knees, which indicates that even a partial replacement introduces some kinematic alterations and instability.
Okay, let's move from AP translation, which is primarily rolling and gliding, to axial rotation. This is the screw-home mechanism we talked about. This natural internal rotation of the tibia relative to the femur during flexion is absolutely vital for function. Table 17.2 summarizes this data.
The natural knee is a rotational marvel. From full extension to 90 degrees of knee flexion, the average normal knee achieves substantial axial rotation, 17.8 degrees. That rotation unlocks the joint and facilitates deep bending. The ability to twist is critical for pivoting, cutting, and even simple maneuvers like getting into a car.
And what happens when we implant the average TKA?
The TKA subjects, as a group, experience significantly less average axial rotation, a paltry 4.8 degrees.
Wow, less than a third of the natural motion.
It's a severe reduction.
Yeah.
And that reduction in twist is the biomechanical explanation for why TKA patients often feel stiff or report difficulty with activities that require rotation.
So the implant is essentially functioning like a hinge that doesn't twist enough and that forces the rotational stress onto the hip, the ankle, or the implant bone interface itself.
Exactly. And again, the variability between implant types is massive, highlighting the design sensitivity. We saw the bicruciate stabilizing, the BCSF TKA, achieve the best AP rollback, and it also performs significantly better in rotation, averaging 10.7 degrees. It maintains a functional amount of rotation, which suggests the highly conforming geometry successfully guides the rotation as well as the rollback.
But then you look at the other end of the spectrum, which design performed the worst rotationally?
That would be the posterior cruciate substituting, mobile bearing, or PCSM TKA. It's meant to provide maximum freedom, but it averaged only 3.3 degrees of rotation.
That's almost zero twist.
It's practically nothing. A rigid knee is a dysfunctional knee, regardless of the implant type. It suggests that while the mobile bearing allows for freedom, the cam and post mechanism is excessively restrictive, or the soft tissues are poorly balanced, preventing that natural twist.
And beyond just the simple reduction in rotation, we also see something troubling. Greater magnitudes of reverse axial rotation. What does reverse rotation imply for the health of the joint?
Reverse axial rotation means the implant is rotating unnaturally. against the typical physiological biomechanics of the joint. The maximum average reverse rotation for all TKAs was minus 19 degrees.
That is dramatically higher than the minus 7.3 degrees we see in normal knees.
It is. It's a massive compensation. The implant geometry is actively fighting the natural internal rotation needed for flexion, and the body is trying to torque the joint to compensate, which potentially generates these unnatural shear stresses.
It creates unnecessary joint stress.
It does. If the components are designed to restrict rotation, that rotational energy has to go somewhere, and it transmits directly into the fixation interface between the implant and the bone, or it increases localized stress on the polyethylene, another major factor in early failure.
This brings us perfectly to the ultimate consequence of poor kinematics, condylar liftoff. This isn't just poor function, this is a catastrophic wear catalyst.
Correct. Liftoff occurs when one condyle loses contact with the tibial bearing surface, and that means the entire physiological load is suddenly transmitted through this single remaining condyle.
So if the load is localized to a single small point, the contact stresses between the femoral component and the polyethylene bearing are essentially doubled.
Exactly. And contact stress is the primary driver of polyethylene wear. Doubled stress leads to a proportional massive increase in the rate of wear. It generates debris that contributes to osteolysis, loosening, and eventual implant failure. This is what historically killed our implants prematurely.
I know some of the older studies showed that liftoff frequency used to be terrifyingly high, sometimes reported at almost 70%. What was the primary driver of that failure rate?
The primary drivers were rudimentary implant designs combined with suboptimal surgical technique, particularly poor soft tissue and ligament balancing. If the flexion gap was too loose medially, or the extension gap is too tight laterally, the knee would be forced into an unnatural kinematic path, guaranteeing liftoff in specific degrees of flexion.
But the data suggests that with better diagnostic tools like fluoroscopy, combined with improved surgical methods, we're finally seeing a reduction in this critical wear mechanism.
We are learning. Fluroscopy identified when and why liftoff occurred, and that allowed surgeons to adapt. For instance, studies by Danes and others highlighted the specific technical importance of ligament balancing protocols, whether you're using gap balancing or measured resection in ensuring even load distribution and preventing liftoff.
So we've moved from just identifying the problem to actually correcting the technique. What does the modern data show regarding the incidence of liftoff?
Well, referencing Andersley's 2011 data, they found that even with modern techniques, 12.3% of 284 TKA subjects still experience some degree of liftoff during dynamic activity.
And that's important because they found this occurred regardless of the patient's BMI. It's a kinematic or technique problem, not just a load-bearing one.
That's a key clinical finding. You can't blame obesity alone for the liftoff. The surgical or design geometry is fundamentally flawed for that specific individual. However, we have very promising results for specialized designs. The work by LaCour in 2014, focusing on specific modern rotating platform TKAs, reported 0 patients experiencing condylar liftoff at 10 years postoperatively.
0 patients. That's incredible.
It is. It confirms that highly conforming, well-balanced, and well-tracked mobile bearings can effectively distribute stress and prevent the doubling of wear that traditionally led to revision surgery. The difference between 70% incidence and 0% incidence is the quantifiable progress driven directly by these fluoroscopic studies.
All right, let's synthesize what this deep dive has revealed. Fluoroscopic analysis provides the undeniable objective proof that the TKA, on average, provides significantly less motion, less natural axial rotation, and a higher probability of pathological movement, like that paradoxical anterior slide compared to a normal knee.
That's right.
And crucially, we've learned that these kinematic deficiencies are not random. They are heavily dependent on the specific implant design philosophy.
The data clearly shows the trade-offs. Designs that rely on soft tissue balance and PCL retention, like the PCRF and PCRM, they exhibit high variability and a high rate of dangerous paradoxical anterior slide. Conversely, the highly constrained bicruciate stabilizing fixed bearing, the BCSF TKA, achieved the best AP rollback and the highest TKA rotation,
Suggesting that enforcing the kinematics mechanically can lead to results that closely mimic or even surpass the metrics of the average native knee.
It can. The clinical relevance of this is enormous. The highly accurate and minimally invasive nature of fluoroscopy provides the foundational in vivo information that drives the entire cycle of orthopedic innovation.
So surgeons use this data to refine gap balancing and instrumentation.
And implant companies use the data to correct flawed geometries and develop new components. The advancements, from simulated annealing registration to the mobile tracking fluoroscope systems, they just promise even greater accuracy and a truer representation of daily function.
It really feels like we're witnessing a fundamental philosophical shift in orthopedics. We're moving beyond simply achieving fixation and range of motion to actively restoring the natural biomechanics.
That's the goal. This fluoroscopic knowledge dictates not only patient satisfaction, but the long-term durability and survival of our implants.
And as we close this deep dive, let's leave you with the provocative question we raised earlier, underpinned by all this comprehensive data. If our objective, quantifiable fluoroscopic data consistently demonstrates that highly constrained TKA designs, like the BCSF, achieve superior near-native AP rollback and rotational metrics compared to less constrained PCL retaining or standard PS designs, where should our design focus lie?
Is the future of replacement surgery maximizing mechanical constraint to force optimal, natural motion patterns, thereby reducing the reliance on variable and often imperfect soft tissue balancing? Or should we continue striving for minimally constrained designs that theoretically provide more freedom, knowing that this freedom currently comes with higher kinematic variability, greater risk of paradoxical slide, and potentially higher rates of early wear? It's the ultimate trade-off: enforced function versus design freedom. And the data from fluoroscopy is forcing us to choose.